Okay, young people, here, let me take my face away. I don't need to see me. Okay. Today we're going to be talking about the types of chemical reactions that we can have, and there are 5 general types that we're going to be talking about right now. And the first type is combustion reactions. Combustion reactions occur when oxygen reacts with what we call a hydrocarbon, and it produces water and some carbon-oxygen containing compound. Okay, hydrocarbons are compounds that contain carbon, hydrogen, and sometimes oxygen every once in a while. Okay. Example, complete combustion is when we have C10H8 combining together with oxygen to make carbon dioxide and water. That would be complete. Carbon dioxide is not poisonous. It is very, very unpoisonous. I'm sorry, that shouldn't have happened. It's very not poisonous. So CO2 is a non-poisonous gas. And so complete combustion makes CO2, but incomplete combustion makes this gas. And this gas is carbon monoxide. Some of you have heard of carbon monoxide. It's a poison. It's a silent poison because it's clear and colorless, and it just doesn't quite work that way. It just replaces oxygen, and it will eventually kill you, and it's very dangerous. So this is the reaction that we really want to happen. This is a reaction that sometimes happens. So what does complete combustion look like? Well, you've seen this. You've seen a Bunsen burner that's working properly. You notice that you have the 2 cones, the nice blue flame that's very consistent. This is what complete combustion looks like in our Bunsen burner. And this is what we have. Methane gas plus oxygen yields carbon dioxide and water. And remember, it's gaseous because it's pretty hot, so you don't see the water. But every time we burn in the lab, we burn the gas that we have, we're creating this, okay? What does incomplete combustion look like? You've seen this as well. Look at that flame. That's a flame that's produced when you don't have enough oxygen, when you're not getting the right mixture so that it burns really well and it burns completely. And so when you're in the lab, if you don't have the proper flame, you're making carbon monoxide, which then eventually could poison us. So you always need to make sure that you have the proper flame. So this is the reaction. We have methane and oxygen produces carbon monoxide and water. It's very similar, but carbon monoxide is the poison, carbon dioxide is not. All right, next kind of reaction, synthesis, or sometimes also called combination. I usually don't use combination because it sounds too much like combustion, so I avoid that, but some of you did learn it like that, so it's not a big deal. I just want to make sure that you know, and if I can't tell the difference between combination and combustion in your handwriting, that will not be a good situation for you. So please make sure that you're writing correctly. So synthesis, basically a combination of 2 or more substances to form a single substance. The key here is that we have only one product. There's only one thing produced, and that's all that will ever be produced if it's a synthesis reaction. Okay, generic of a synthesis reaction is A plus B, 2 little parts going to an AB, something that is more complex, but there's only one of them. So here we go. We see it in the form of little dots here, little particles. We see the red particle and the yellow particle on the reactant side, and then on the product side, we see them bonded together as a single compound. Okay? So example, 2Cu plus O2 yields 2CuO. The 2's are when we balance. Remember that from the last video. Okay? So what does a synthesis reaction look like? Well, here we are. We have 2 things. We have hydrogen gas and chlorine gas. And hydrogen gas and chlorine gas are being put together. So here's the hydrogen gas going in. The chlorine gas is right here. And then what we see in the end is we see where it's forming right here. This little white thing is forming hydrogen chloride gas, or it's actually hydrochloric acid gas. Okay? So there we go. H2, which is what we have here. Cl2, which is the chlorine gas, and it produces these things right here where it's a little white part. There, see that little white speck right there as you're coming down the tube? Right there, okay? Decomposition is the next kind of reaction. Decomposition is a breakdown reaction. We have something that is big breaking down into 2 or more simpler substances. So the key here is that we only have one reactant. I feel like synthesis and decomposition reactions are the easiest to recognize. because there's only one product in a synthesis, there's only one reactant in a decomposition. So it automatically should clue you off, okay? So generic, AB, something complicated or complex, breaking down to A plus B, which are the more simplistic forms of those. And then we see the red and yellow together, breaking apart into red particle and a yellow particle. So we get the idea. Examples. Now, decompositions are a little more complicated because of the examples, because of what happens when the breakdown. So if we have water breaking down into hydrogen and oxygen, that's a decomposition of a binary compound. So if you have a binary compound, the only thing it can decompose into is its elements. That makes sense, right? Okay, if I have a carbonate, like hydrogen carbonate or carbonic acid, this is the decomposition of a carbonate, because what happens is we take this one single reactant and we break it down into water and carbon dioxide. They're not elements, but they're smaller pieces of what the carbonic acid was made out of. But a carbonate will always produce carbon dioxide. So if you have a carbonate decomposing, it's going to produce carbon dioxide. Chlorates, like potassium chlorate. If I heat potassium chlorate, I'm going to give off oxygen gas, and I'm going to keep potassium chloride, which is a salt. So decomposition of a chlorate always produces oxygen and the chloride salt. Hydroxide, if I have magnesium hydroxide and I heat it up, I'm going to get magnesium oxide and water in gaseous form. And this always happens when we have the decomposition of hydroxide. So these are kind of important because these tell you, these items right here tell you what happens in specific situations. So we don't always just see binary compounds. Sometimes we see other things as well. Okay, so decomposition reaction. Here we have liquid water down here. Right here, liquid water. And it's being electrocuted. You see the lead here and the lead here. Okay. And in those leads, it's being, the electricity is being passed through the water. And you can see up here in the spaces, we have something being made. And hydrogen and oxygen are the things that are being made. So we can actually tell which test tube is making which based upon its balancing. So we see that we have 2 hydrogen to 1 oxygen. So this is the hydrogen and this is the oxygen. And we'll talk a little bit later about how we also can know that. Okay. Single replacement is the 4th kind. This occurs when a single element reacts with an ionic compound. And it's pretty important most of the time, like 90–95% of the time, you're going to have an ionic compound. Every once in a while, we see a covalent. Every once in a while, every great once in a while. Water is one of those that we see a covalent compound instead of ionic. Okay, so an ionic compound, one of the elements in the ionic compound switches places with the element that's by itself. So you have an element by itself, a single, replacing one of the pieces in an ionic compound. So I have 2 forms of this. I have what I can have a metal, right, replacing B. And we get B plus MC. One thing is being replaced. So we see the purple ball replacing the red ball. And now we have purple and yellow together and red by itself. Single replacement. We have a single replacing a single. And that single is popping out to be by itself, still a single. And now we have a new couple. Okay. Ionic compounds are really special. And I know in class, and this is going to sound really, really jerky, and it's not meant to sound jerky. It's not meant to even sound, you know, a little bit because I am not at all. But ionic bonds are actually homophobic. Now, don't think about homophobic in a sexual way, because I want you to understand when we talk about homo means the same. Ionic bonds are made of cations and anions. They're opposites. So opposites always want to be with opposites because likes repel. They won't stay together if they're with something that's like them. So we always have to have opposites. So ionic bonds are slightly homophobic because they want things that are opposite them. They like to be heterogeneous. They like to be different, the 2 things to be different. They like cations and anions together. They don't like cations and cations or anions and anions. So it really makes a difference what that single is. And so we'll see in this next one This next equation here, we see that the single does make a difference. Look at here. We have an A. A is replacing C. So A must be something that forms an anion, because that's the only thing that A can replace. And we can see the green replaces the yellow. Now we have yellow by itself, and we have a new compound with the green guy as the anion. So how is this different from the last example? Well, A can only replace C, M could only replace B, and so therefore we get something that is a little different each time, because ionic bonds are truly homophobic when it comes to the substances they work with. They will only work with substances who are opposite them. Okay? So single replacement. General form, we have AB plus C goes to AC plus B. Okay, that's called cation replacement. Because A or C, that's not true. That's actually called anion replacement. Sorry about that. So we have AB plus D gives you AD plus B. Well, that's interesting because both of those show the same thing, and that's not quite right. So let's just move on from here, okay? Here, cation replacement involves the replacement. You have a metal or something forming a cation, replacing the cation, okay? And then we have a metal by itself again and a new cation. In anion replacement, we have an anion. Chlorine is always going to form an anion, replacing the anion. Then bromine comes out. We now have a new element and a new anion in our compound, okay? A single replacement reaction. This is showing copper wire up here, a copper metal mesh, right? And it's being introduced into what we call silver nitrate solution. So we see silver atoms here, and then we see the nitrate groups right there, and then we see the water. So this is water, the little Mickey Mouse ears are water. So that's what we see there. And what's happening is over time, you see bubbling, you see, a lot of stuff going on. Actually, you don't see bubbling. What you see is you see like furry stuff that looks like, and you see no wire down here, but you see furry stuff all over there. Well, that furry stuff is now silver metal. And now what we see is we see copper ions in with nitrate ions as well as your water, okay? So that is that reaction. Copper plus silver nitrate yields copper nitrate and silver solid, right? Double replacement reactions. Two ions and two compounds change partners. Basically here, we have two ionic compounds. So what we just basically say is they switch partners, and now we have two new compounds made of the same four substances. They've just switched partners. So here we go. AD plus BC yields AC plus BD. We've switched C and D. It doesn't really matter if you say you switch C and D or you switch B and A. It doesn't matter as long as you're only switching one of the partners for the other partner of the same thing. So remember, you can't switch A for C or B for D. You can only switch A for B or D for C. One of the two, but I say DC, so it doesn't really matter though. So we can see this. We can see D coming in and replacing A, and then our C, and then C coming in and replacing D. So now we have purple and yellow and red and green. Okay? So double replacement reaction. We have lead nitrate over here, and we have potassium iodide over here. And when we put them together, we get a solid. This solid, our potassium chromate, this solid that we get is lead chromate, okay? So it's kind of pretty cool, actually. All right. So usually we know a double replacement reaction occurs because a precipitate is formed. In special double replacement reactions called acid-base reactions, we know they occur when color change happens. So, but precipitate is usually the thing that we look for in a double replacement reaction. Okay, steps to classifying reactions. Does the reaction contain oxygen, carbon dioxide, or water? If it does, then it's combustion. Do simple molecules form one more complicated product? If yes, it's a synthesis. Does a single reactant break apart into two or more simpler products? If yes, then it's decomposition. Is there an ionic compound in a single element on the reactant side and product side? Then it's single replacement. Are all compounds ionic? then it's double replacement. So some really simple steps to kind of identify if you think about the questions you have to be asked. Examples. Here we have one C3H7OH plus O2 yields CO2 and water. What kind is that? Yeah, it's combustion. Next one. Mg plus O2 gives MgO. Synthesis. Good job. Next one. H2O2 yields H2O plus O2. Yeah, that's decomposition. We start with one single reactant. Next one. Cu plus HNO3 yields H2 plus CuNO3. Yep. Single replacement. This reaction is really bad though because it doesn't really work like that. Something else happens. Something else happens with this. This part, the NO3 part, decomposes a little bit. And then finally, PbNO3 plus Ki. Yeah, double replacement. Okay. It says displacement, replacement. It doesn't matter. I use replacement. It doesn't really matter. Okay. Thank you.